Evening, everyone. My name is Stoyan, and I'm a senior 3D tech artist here at SpaceApe. And I'm here to present you the Uber shader we've been working on for the past few months. Before we start, how many of you here have ever created a shader? Don't be shy, even something created in the new node-based shader editor counts. All right, cool. So about like a third. Cool. So before we start, I just want to cover what we're going to go through. I'm going to start with a bit of an introduction at first, and then we're going to go through the shader structure and how we structured everything in terms of files. The global effects we created because we use a shader on everything, the same shader on absolutely everything, so that allows us to do some neat global effects such as fog. The different lighting models, because we have multiple games and they all have different art styles, so we needed different lighting models depending on the style we're going for. And we're going to conclude at the end. Now, an Uber shader is it's a normal shader that can do a lot of different things. And why did we create it? The main reason is because we have a lot of different projects, we have a lot of different prototypes, and not that many tech artists or people that are brave enough to write a shader. So we wanted something that's scalable as well, because we distribute games on the lowest end devices to some shiny new phones, and we needed something that can scale on everything. It also enables us to use global effects. It's very important. So when you have the same shader and everything, you can do all kinds of cool things, which we'll show later. And we wanted a lot of freedom for our direction as well. So the different lighting models definitely help with that. All right, so let's go through the shader structure. How many of you, okay, so let's go through this. So shading models, CGInk is a file that you import into your shader. And a CGInk just contains some codes and functions that you can use. And in this case, all of our calculations are done in there. So stuff like reflections or specular is done in that file. And we also have a few macros that do global effects. And you can see we have fog, shadows, and post-processing, sorry. And then in the Uber shader CGInk, we get all these functions that we had before. So all the work is done there. And then we just combine them into a vertex and a fragment shader. A vertex shader executes on every single vert that you see on the screen, and a fragment shader executes on every single pixel. So whatever you do in the vertex shader is much, much cheaper. So it's advisable to do everything there. And of course, we determine how different lighting models interact. And this is useful because anybody can create a shader from these functions on the left, and all the shaders will look identical, or at least have like similar lighting models. And finally, in the actual shader file, we have our inspector variables, and we have 4 different LODs, so for 4 different quality levels. And this is where we define our shader features. I'll explain what a shader feature is next. A shader feature is a keyword that you use to remove or add code into your shaders. Now, I don't know if you noticed, but in shaders, if flow control is not that efficient. So the only way to remove code from it or make it not run is just actually remove it. So we use these shader keywords. So for example, we have use for now here, and if we disable that keyword, the for now code is just going to not be in the shader. And that way you can create your own shader, very similar to how ShaderForge does it. But you do it with this kind of UI. So every single tick box or every single drop-down activates or deactivates keywords, and that in turn creates code for you. All right, so how do we do the scaling? In the final shader, we have 4 subshaders, each with a different LOD number. And on the ultra LOD, we have absolutely everything enabled. And very expensive things as well, like normal maps and reflections. And we have everything calculated per pixel, so it is expensive. We only use this on high-end devices and characters, something that's the center of attention. And then on the high one, we remove the normal maps and the reflections. And this is the difference. This is just looking at reflection just disappearing. But this way you can have the same shader on absolutely everything. And depending on the device, it's going to appear in different ways. But it's still going to run at, say, 60 FPS or 30 FPS, depending on what you're targeting. Next, we have medium, so we removed some more features. And down to low, everything is calculated per vertex, not per pixel. And you can see the difference here. The specular highlight is quite angular. And that is because it's being calculated per vertex, and this is a fairly low poly model. And we go down to just diffuse lighting, and it's very basic, but it runs very, very fast. So having the same shader on everything allows us to do some interesting global effects, the first of which is converting to linear. I'm not going to go too much in depth of what is gamma and what is linear and why you need it, but basically it's the way that colors and lighting is being calculated and then presented to you on the screen. The one that looks better for sure is the second one. So the second one is linear, and it's mathematically correct. This is what you get in the real world. The first one, that is the standard default Unity version of things. You can switch to linear in Unity by default, but that conversion is done in the hardware, and a lot of devices still don't support that out of the box. So the way we approach it, so this is a character model by Andrew Johnston. He's one of our lead artists here. And this is the difference that linear conversion makes. So you can see the lighting is much less harsh, and the reflections layer very nicely on top of the arm. So that is a mathematically correct way of doing things. Although if the art direction requires the harsher lighting, of course you're going to go for gamma. And the way we did it is simply in the shader. So every single color input, we convert it to linear. And for the final output of the shader, so when we return a final color, we do linear to gamma. And to simplify things, we just use simple multiplication or square roots. We didn't use the power function. Power function is expensive. It's kind of an approximation, but visually it makes almost no difference. Another global effect we added was color correction. Now, color correction traditionally is done as a post effect. You capture the whole screen as a texture, and then you apply a shader on it, but that is really, really expensive, especially if you have a 4K phone or something crazy like that. It's a lot of pixels to process. Instead, we just do it on the shader level. And you can see here, the color correction is actually done in Photoshop. Kind of like magic. So you extract the color correction from Photoshop, and then you can rotate around it. It's exactly the same as the one you did in Photoshop. Of course, the sky is not affected because that's still the Unity standard sky system. So the way that was done, every time you capture a screenshot with the tool, it creates that little gradient at the bottom left corner. Then we go into Photoshop, and when we adjust the colors, the gradient adjusts in turn as well. And we get that gradient, we extract it afterwards, and we run this code through it. This basically remaps every single channel to the gradients, and you get the exact same color correction. This is a little bit limited. You can't desaturate images, you can't saturate them more, but you can use curves or levels if you're familiar with those Photoshop tools. It's very, very cheap because it runs on the shader level, but it's not free. Of course, you're still doing 3 texture reads. It's not free, but on high-end devices, it should run like very smoothly. Next global effect we added is fog. Fog is supported by Unity as well. It's done in the vertex shader, so it's extremely cheap. And what you're seeing here is very, very similar to what Unity has already. You can have some fog, adjust the distance, adjust the color. What we made differently, though, is we added some height fog as well. So this is still done in the vertex shader. There's no post effects whatsoever. And you can adjust the density of it, the height of it. Gives you these nice atmospherics. And at the top of that, we added some sun scattering. So this is done very simply. I'll show you later the equation for this. But it just creates this nice and atmospheric look of it. And it's still all calculated in the vertex shader. It's very, very cheap, but makes your game look a lot more lifelike. Kind of looks like Horizon Zero Dawn, even though it's running on a Galaxy S4. All right. So, I exaggerated the colors a little bit so you can see what's happening. All we did was we grabbed the camera direction and the sun direction, so that's your directional lights, and the dot product of it is what you see. So we layer between 2 colors. You can adjust any kind of color you want. The sun could be purple and your sky could be red, exactly the opposite of this. And we run it through a power function. Like I mentioned, it is expensive, but if you run it on the vertex shader, it's actually pretty good to kind of adjust the width of that sun. So the next thing we added, you've seen Unity shadows, you used them before. They can be a bit jaggy on mobile. They can be hard to control. They could be quite pixelated. So we implemented our own shadow system that has fading depending on the light angle. So you can see it fades away the longer it is, and it becomes stronger if it's shorter. And the way we did this, we rendered the character from the point of view of the light on a very, very small texture. And we blurred it, added it on top of the Uber shader, and you get this. You can, of course, have sharp shadows if you want to. You can have very soft shadows. And it's very, very cheap because we render only one character on a very small texture. And that is great because a lot of our games just involve like a star character. We do have games like Transformers Earth Wars, they have a lot of characters, but for some of our other games, you can have something, like say, for example, you are doing a game where there's only one character on the screen, you can totally use this technique and save a lot of processing, a lot of memory just to create his shadows, but they look nice and soft. So the way we did it, we have the dot product of the world up vector and then the camera view direction. All right, well basically that gives you a gradient based on the character's height. And then we have a simple blur. Blurs can be really, really expensive because you're doing 9 texture reads. But since it's a very small texture, it's really, really cheap. All right. Now, for lighting models, before I get into those, I want to briefly describe what Lambert and Blind Phong shading is. Lambert shading is when you get the dot product of your normal and your light vectors, and then you get that light fallout that you get on the lower left corner. And specular lighting is calculated, it's a little bit more complicated to calculate. You get the view normal, the light normal, and the half vector between those. The dot product between the half vector and the normal vector gives you specular. A mouthful, but it gives you that little dot at the lower right corner. And we use these formulas and calculations to map a texture around it. So we have this texture that represents the fall off from light to shadow, and you can do absolutely anything with it. So what we did was we added some subsurface scattering, which is really important for characters to look good. So, and we have a rim light at the end as well. And that comes for absolutely free because we're doing all this in a texture. So the way we created this texture is with Substance Designer. The name kind of sounds like you're creating drugs or something, but you're actually creating procedural textures in Substance Designer. Well, it's very useful. You can import a substance file into Unity and in real time adjust the fall off or adjust the nodes that you have exposed there. And you can see we can have some sharp fall-offs, we can have subsurface scattering. You can see this can become softer, more natural. We can have cel-shaded, that's all done in Substance again, no code. And we can adjust the steps. Even the specular highlights are affected by this. You can have a very nice stylized look. And it doesn't end there. Since it's a substance file, any artist can just open it, edit it, and they can create any kind of light fall if they want. Now for specular, that one is a little bit more complicated. What you see on the left is a material scan. So this is what specular highlights look in the real world. And the one we have on the right, Blind Phong, that's the equation I showed you earlier. Now the one in the middle, GGX, that is the standard right now. It's used in ray trace rendering. So you see it in Disney movies, you would see it in the latest AAA games. That is the standard for specular highlights. And that is done using this formula. Now, if you get this formula and if you run for every frame, for every pixel, that can become a little bit expensive. So what we did again, Substance Designer, allows you to actually create textures based on math. So this is just that formula, put it in Substance Designer, and then it gives us this texture, which I also tried to create by hand. And it's really, really difficult. It's like trying to draw a perfect circle on a motorcycle, on a running motorcycle. But yeah, Substance Designer was really, really useful for this. And so we have this texture, and we use the formula we had before, so n.h, and that maps the specular highlights. And we have this really, really nice and natural fall-off, very similar to the Unity standard shader as well. This is the shader in action. So we adjust the smoothness. And you can see you have the effect of energy conservation. The tight hotspot just goes around and distributes along equally. It looks much nicer if you apply specular texture as well. Alrighty. So to conclude, artistic direction is king. So absolutely every single feature of the shader was created by a request from an artist. And me being an artist myself, I put in a lot of those requests, of course. And modularizing your code was very useful because anybody that wanted to create a shader could grab those functions, grab those logo effects, and just apply them to their own shaders. So it made things really easy. Baking as much as you can, having your complicated equations or complicated shading models baked into textures makes everything really, really cheap. And custom shaders on everything also opens up a lot of doors, so I definitely encourage it, even if you use simple ones. Like you have the ultimate control about performance or the look of your games. And thank you. Any questions?
Hello. Hi. The one thing that I'm wondering from the presentation that you showed was when you have an item and the shader is essentially changed, that becomes like a texture slapped onto it, essentially. Is that correct?
That's right.
So how exactly does that work with an interaction of one object to another object? So if you have one object which is meant to be a reflective object, will it reflect light onto another object, or would you need to create a vector and then change that object which is next to it?
Usually real-time objects don't reflect light from each other in games, and you can do that. You can attach normal lights. There is actually a vertex-based four light system in there, so you can have a point light and it can reflect the light. But if you want real-time reflections, that is going into the realm of very, very expensive in kind of console and VR and that kind of stuff. Yeah, thanks.
Hello. So my question is it the open source or it's your internal shader and you don't want to?
Right now, no, it's not open source at the moment. I'm not sure if it ever will be, but we can discuss it. If you want to, if you have any questions, I'll be around. I can tell you everything about it.
This way. So what he said you to render the shadow, you render from the light.
That's right.
Do you just use a Unity camera to really render from that camera and grab
Yes.
something from there? Oh, okay.
Yeah, so it's a Unity camera that renders everything through a replacement shader. So the way the camera sees it, just throw another shader, and then we apply that shader that has the gradient of the character. And then whatever that camera sees, we'll render to a texture, blur it, and then project it on the mesh. And that's pretty much how Unity shadow mapping works as well, just with some other stuff on top.
So don't you have a sort of substructure that doesn't involve the Unity camera necessarily, just a simpler one?
No, it's
so you have to go through the Unity camera structure.
We did need a.
There's no other way around.
You can code your own camera, but the Unity camera has some useful functions. I took the matrices from that, for example. The view and projection matrices, that's what you need to project the shadow on. It just made things easier, but you can totally code your own camera or your own kind of light.
Thanks.
Hello again.
Hi.
So when you were at the beginning of the talk, you were showing some thresholds of the performance, and the first thing you sacrificed was the reflection. Did you ever consider image-based lighting to restore the functionality partially of the reflection? But still, it's going to be so much cheaper.
So with reflections, we do have image-based lighting and the vertex shader for the Uber shader. But for reflections, we need stuff like the arm of the character you just saw, like something that's really, really sharp. And just using the reflection probes, I found just adds like 30 or 40 instructions on top. And you can use cube maps. Cube maps are a bit cheaper, but they don't really have that smoothness factor. You can't really blur them. Sorry, does that answer your question?
So you say about that you use Substance Designer and you write your own shaders. Like, do you usually write your own, or do you just use a Substance Designer shaders output?
So we use Substance Designer to create the textures for the shader itself. The shaders are all written from scratch, although I did use Shader Forge to just kind of prototype things before that. But Yeah, Substance Designer just creates a texture for you. If you can create textures in C#, but it's not as artist friendly, I find, and it might not be as fast as Substance Designer. Any more questions?
Thank you very much.
All right, thank you guys.